everyone, I'm Shashank from India and today I'll be talking about particle physics. First of all, what is particle physics? Particle physics is a branch of physics that deals with the study and the properties of particles that constitute radiation and matter. The idea is that everything in this universe is made up of atoms. This idea of atoms dates back to nearly 6th century BC. In the 19th century, John Dalton concluded that every element in the universe is made up of atoms. But is that true? Is atom the fundamental building block of the universe? However, atom means that it's indivisible, that is, it cannot be divided and is the fundamental building block of the universe. But it isn't true. Experiments of scattering and radioactivity show that an atom is made up of three subatomic particles. They are the proton, neutron and electron. The neutron, as its name suggests, is electrically neutral, that is, it does not have any charge. But the proton and the electron have charges. The electron has a charge of about minus 1.602 times 10 to the minus 19 power coulombs. The proton has a charge of about positive 1.602 times 10 to the power of negative 19 coulombs. The proton and the neutron have about the same mass but are very heavy when compared to the tiny electron. The proton and the neutron form the nucleus and are together called as nucleons, and the electron orbits the nucleus in orbitals. But this is not the end of the journey. Do you think that these subatomic particles are made up of even more particles? I hope that you have paused the video and given a try at it. The answer is yes. After the discovery of the proton and neutron, scientists found a whole zoo of particles which were extremely short-lived. These were found by studying cosmic rays, high-energy particles from space which collide with the matter on Earth. The first few of them were positron, which was the positive version of the electron, then followed the muon, which was similar to the electron but with more mass, and then came the mesons and the neutrinos. The physicists realized the need of a mathematical model that would describe all these particles and their interaction and relationships with the four fundamental forces: the gravitational force, the electromagnetic force, the weak nuclear force and the strong nuclear force. They had the idea that these particles were made up of even smaller subunits called quarks. At first they thought that this was just a mathematical idea, but then they realized that it was true. Then a theory was developed in which these particles were classified on the basis of the mathematics. Then this theory developed into what we today call as the Standard Model. So here you can see the equation of the Standard Model. This has everything that we know about physics and it describes the particles with such accuracy. But it does not describe the gravitational force and some other smaller concepts. Up until now, we have discovered 61 particles and they are divided into two categories: the fermions, which follow the Fermi-Dirac statistics, and the bosons, which follow the Bose-Einstein statistics. Here you can see the first set of particles, the quarks. The quarks come in six flavors: up, down, top, down, strange and charm. They combine together and form composite particles called hadrons. When a particle is made up of three quarks, it is called a baryon, and when it is made up of a quark and an anti-quark pair, it is called a meson. The top quark is heaviest among the six. The heavier quarks degenerate into smaller up and down quarks through a process called particle decay. And we'll be studying about particle decay in the further video. Then you can see the leptons, which are another class of particles. The leptons also come in six flavors like the quarks, which are the electrons, muons, the tau particles, electron neutrinos, muon neutrinos, and the tau neutrinos. The charged leptons combine to form more composite particles, but the neutrinos rarely interact with anything, so they are rarely observed. They are also divided into some other categories. The leptons do not interact with the strong nuclear force, but they do interact with the other three. The only exception is the neutrino. Since it is not a charged particle, it does not interact with the electromagnetic force. So let's move on to the next kind of particles, the gauge bosons. They're bosons, unlike the quarks and the electrons that we saw earlier, which are fermions. The gravitational force acts between bodies or particles which are mass. The electromagnetic force acts between charges and is responsible for light, heat radiation, magnetism, and electricity. The strong nuclear force is responsible for holding the quarks inside protons and neutrons and is also responsible for binding the atomic nuclei. The weak nuclear force is responsible for beta radioactive decay, in which unstable atoms degenerate into smaller atoms when they emit other smaller particles like electrons. But the scientists were not able to understand how these forces worked. So new theory was developed in which these forces acted through messenger particles. The messenger particle of electromagnetic force is photon, the particle of light. The messenger particle of the weak nuclear force are W and Z bosons. On the other hand, the messenger particle of the strong nuclear force is the gluons, which hold the quarks inside baryons. And the messenger particle of the gravitational force is the graviton, which is hypothetical and its existence has not yet been confirmed. But there remains another major question. How do particles get their mass? A famous physicist called Peter Higgs developed a theory in which if particles interact with the everywhere permeating energetic Higgs fields, they get mass. The more they interact, the more mass they get. So photons do not interact with the Higgs field much, so they have no mass. Whereas the top quark is the heaviest among the quarks, interacts much more with the Higgs field than the photon, so it has more mass. To conceptualize this concept, you can imagine a pool of honey which has the Higgs field and you being the swimmer in it as the particle. You'd feel difficult to swim in it and would feel that you are much more heavy than in the normal situation. This in the similar way also Higgs field works, but Peter Higgs also predicted that the Higgs field also give rise to a particle of its own kind, the Higgs boson. Scientists have been trying to find the Higgs boson in particle accelerators like the Large Hadron Collider. So next move on to the next class of particles, which is entirely different from the original ones. They are called the antiparticles or the antimatter. They have the same properties of the matter, but they have the opposite electrical charge. For example, the positron, which is the antimatter of the antiparticle of the electron, has positive charge, whereas the electron has negative charge. This idea was proposed by Paul Dirac when he was studying his solutions of his equations, which were used to describe electrons moving at relativistic speeds. When a particle and its corresponding antiparticle meet, they annihilate. They give huge amounts of energy in the form of heat and light. But these particles are made from high energy collisions. How are these collisions studied? The answer came in the form of Feynman diagrams. These diagrams were invented by Richard Feynman. These diagrams graphically represent the collision between particles and the products produced from them, and they also represent the decay of unstable particles. So here you can see the two electrons interacting. The two electrons are approaching together and they are moving in time, and when they come together they share a photon and they move apart. So here you can see other complicated Feynman diagrams. So that's the major concepts of particle physics. I hope that you have understood that. Thank you.